Fine, good morning, one and all present here. Special good morning to Mr. Bobin T. Price, Professor EC, Mar Ibrahim College of Engineering, Martandam. And on behalf of AICTE Prerana Day 14, and on behalf of Francis Xavier Engineering College and my own behalf, I welcome you, sir, for the presentation. I welcome all my students for the session. Okay, so I request before we start the session, I request Gerlin Christina Grace to post a prayer.
Prayer. Almighty God, we thank you for this wonderful day. Be with us throughout this day. We thank you, Lord, for the gift of education that you have given us. Help us to study well and get good marks. Grant us the strength to overcome temptations. Help us to be pure in thought, word, and deed. Bless all our faculty members and our parents. We ask all these in the name of our Lord Jesus Christ. Amen.
Thank you, Gerlin, for your wonderful daily prayer. Okay, thanks a lot for that. And I request Mr. Bobin T. Price sir to take a session, sir. Thank you.
Thank you, Suresh, sir. Good morning to one and all present here. So mostly the students might be familiar with me, myself Bobin T. Price, working as in the School of ECE, Mar Ibrahim College of Engineering, Ilavulai, Martandam. So this is today's session will be a continuation of the previous session, am I right? The semiconductor theory. Whether I am clear or audible, you can type in the message. Whether I am audible to everyone, just type yes or no. Whether I am audible to everyone, yes. Thank you. Are you able to see the screen now? Are you able to see the screen now? Yeah. Fine, thank you. So I take this opportunity to thank once again the management and the administration people, and especially the coordinate the program, that is AICTE Prerana Scheme. The AICTE sponsored free GATE coaching for SCST students for the academic year 2019-20 and 2020-21. And especially I'm concentrating on the semiconductor theory concepts. Already we finished the one session and we are going to continue the same. Today, we are going to see, so first of all, about the revision of the previous lecture. So I am sure that most of the people are, yes, Aisha, Fatimos, Ramesh, Ramakrishnan, okay. I am sure that more the students are from the previous lecture, the continuation is coming, right? So the revision of the last lecture is started from first the semiconductor basics. So there we are dealing with the temperature, that is the conversion of temperature from Kelvin to degree Celsius, and then the degree Celsius to Kelvin. With respect to that, in the next step, we are dealing with the thermal voltage, VT. So what is the K, what is T, how the Planck's constant is taking influence on the different values, what is the joule value, and what is the electron volt value. So all the basic things we come across that. And the next step, we move to the mobility of the charge carrier. So depend upon the mobility, how the electric current or the diffusion or drift current is creating impact in the electronic devices, and how it is going to change the pattern of movement from one time to the higher concentration to the lower concentration area, and how this diffusion current is able to impact the weightage or designing of the very large scale devices. For example, the concept of VLSI or the multi-scale integration, the movement of these charge particles are playing a major role. Next, in the carrier transport, the major two concepts we are dealing with this one is diffusion current and the drift current. One is diffusion current and another one is drift current. So as I said earlier, diffusion current is not applied by any external force. As the drift current, we are applying some external electric field. Due to that motion or that force, the motion of charge carriers occur, and depending upon the charge carriers, we are able to we are able to get the current value. Next is energy band diagram. So here we had a detailed study about the intrinsic and extrinsic semiconductor and how this energy band gap is creating impacts, right? And depending upon the energy band gap, we are able to define the properties of the body, whether it is semiconductor or conductor or insulator, all the things we have been dealt with. And how the movement is happening between, or the movement of electrons from covalent bond to conduction bond, or conduction bond to valence band to conduction bond, and conduction bond to covalent bond. How it is happening, we are also seen really in the clear way. And the final is the Poisson and continuity equation. As I said earlier, this Poisson and continuity equation are dealt with different areas like thermodynamics or fluid dynamics, and continue in a way in our electronic movement, that is the charge particle movement also. So how these concepts or the semiconductor theory part 1 is creating an impact in the gate. Depending upon that, we solved so many already asked questions in the gate syllabus or the gate question paper, and we solved continuously with a good answer and a reply from you also, right? So in my concern or my knowledge, I take it into account that you have some clear knowledge about this. Okay. So regarding this, I mentioned that please bring calculator and the note pen. I am sure that people are having calculator right now, right? So with that knowledge, we are going with some example what we discussed in the earlier class. The discussion in the example is the neural base width of a bipolar transistor biased in the active region is 0.8 micrometer. The maximum electron concentration and the diffusion constant in the base are 10 power 14 per centimeter cube. And dn is equal to 32 centimeter squared per second respectively. Assuming negligible recombination, I, the base, the collector current, so the collector current density is the question mark, and the provided value is total charge. Can I get answer from you guys? Can I get answer? The same problem, same ditto problem with the change in value we worked out in the last class. Within 2 minutes, I am expecting answers from you. Guys, write down the simple formula for the collector current density. That is the current density value J. You are going to find the value of J. No response. That's probably forget all those things, huh? So the thing is, the given value dn is equal to 32 centimeters squared per second, and the intrinsic concentration, that is the pure concentration, n is equal to 10 power 14 per centimeter cube. The base width is 0.8 micrometer. Did anyone get the answer? No, not yet. So the solution is current density Jc is equal to q dot dn by dx. Q dot dn by dx. You know the value of q, that is 1.6 into 10 power minus 19. 1.6 into 10 to the power of minus 19. into 32 into 10 to the power of 14 divided by 0.8 into 10 to the power of minus 4. Keep it in account that value is not meter, it is centimeter. Okay, so I change it to 0.8 into 10 to the power of minus 4. Usually micrometer means you will mention like 10 power minus 6, but it is centimeter. You want to convert the same in the form of centimeter. So the answer is JC is equal to 6.4 ampere per centimeter square. Sorry, don't get the answer right. Okay, so do you have any doubts regarding this? Do you have any doubt? Guys, use the chat window please, or open the mic. Regarding this, any doubt? No. So the next one is also the one I mentioned in the previous class. That is the intrinsic carrier concentration of silicon sample at 300 Kelvin is 1.6 into 10 to the power of 16 per meter cube. If after doping the number of majority carrier is 16 into 10 to the power of 20 per meter cube, the minority carrier density is. Once again repeating, the intrinsic carrier concentration of silicon sample at 300 Kelvin is 1.6 into 10 to the power of 16 per meter cube. After doping, the number of majority carrier is 16 into 10 to the power of 20 per meter cube. The minority carrier density is. Can I get any answer? Aisha Fatima. Aisha Fatima, you can open your mic. Whether it's audible or, yeah. Did you get the answer? Hello? Whether it's audible to me? I'm not sure about this. Whether it's audible? It's okay. The thing is, did anyone get the answer, Mark? Anyone? If you have some continuation means that will be fine. Not so, it will be a boring class. Okay. So the given value is T is equal to 300 Kelvin, Na is equal to 1.6 into 10 to the power of 16 per meter cube, Na is equal to 16 into 10 to the power of 20 per meter cube. That is the provided value. So the minority carrier density is equal to Na square divided by Na, which is equal to 1.6 into 10 to the power of 16 the whole square divided by 16 into 10 power 20. By substituting the values, you will get an answer like 0.16 into 10 to the power of 12 per meter cube. Okay. So the minority density is equal to 16 into 10 to the power of 10 per meter cube. So this is the answer. So why I mentioned for the revision is, if you have some continuation or if you have some relation with the previous class only, then that will be easier. Otherwise, it will be somewhat difficult to follow the same. Clear? So overview of the lecture series about today's class. First one is special diodes. So the special diodes, we are going to deal with LED, photodiode, solar cell, and different types of solar cell, including Schottky diodes and Schottky solar cell. Then the Schottky solar cell, and the other one is the I forgot the name. The Schottky solar cell, and another one is I will mention later. So the integrated next the topic is integrated circuit processing. So here we are going to deal with the different process, how the circuit is going to be fabricated. So thermal oxidation, photolithography, etching, dopant diffusion, metal evaporation, electrical testing. So these are the series of steps as an important 8 mark or 30 mark question as you studied earlier. So now we are going to deal with the detailed concepts. Okay, so depending upon the concept, how we are going to face the gate questions we are going to solve. Clear? So first we are going to deal with LED diodes, right? Clear? So what do you mean by LED? What do you mean by LED? You can use the chat window or you can use the mic. I want some answer, otherwise it will be boring, guys, please. If it might be an interactive section only, then it will be fine. Otherwise, it is going to be really boring session. What do you mean by LED? It emits light due to the recombination of carriers. Fine, good answer, fantastic. So this is the correct definition, right? It emits light due to the recombination of carriers or charge carriers. Clear? So a light releasing diode is an electric component that emits light when an electric currents flow through it. So when a current passes through the LED, the electron recombine. This is the word. The electrons recombine with holes emitting light in the process. So the recombination, the combination of electrons and holes are occur. Depending upon the process, we are going to emit some photon energy. We are going to emit some photon energy. Having similar characteristic of PN junction diode. Yes, it is also having the same characteristic feature of a PN junction diode. It is having a P type and an N type. It is having a P type and an N type. So LED allows the flow of current in the forward direction. So here it is the major concept we are going to deal with. It is deal with the forward bias configuration. So next one is the working principle on LED. In the diagram, it is clearly visible that this blue color is representing a P-type material and this yellow color is representing a N-type material. The combining area, this particular area is known as the junction, okay, the recombination junction. Here there is red color dots that are representing the electrons and the white color holes are representing the positive charge particles or nothing else, holes, okay. So the combination of P-type and N-type. The representation of LED is the symbol here, a symbol diode, but the indication of arrow towards the upwards. The indication of arrow towards upwards means that it is glowing. Indication of arrow towards upwards means that it is glowing. Clear? So this is the P-type and N-type. Combination of a P-type and N-type semiconductor will result in the form of LED. So here you are able to see it is biased. It is biased. What is the biased condition here? Can I get any answer? In this diagram, whether it is forward biased or is reverse biased? Forward or reverse biased? See the diagram once more. Whether it is forward or reverse biased. Forward. Good. So the forward bias means the P-type material should be connected at the positive terminal and the N-type material should be connected at the negative terminal. That is what we call as the forward biasing condition. If it is reverse or the vice versa, the operation will be in the inverse form, then we can say it as a reverse bias condition. So in the forward bias condition, when we apply the voltage, when we are applying the voltage, the holes and the electrons are combined. In this second diagram, there is the energy band diagram. You are able to see that the electrons from the upper band will be moving to the lower band, valence band. So these two will be recombined. These two things will be recombined, and some energy will be emitted. Some energy will be emitted. For example, if you are using two stones in the earlier Stone Age in the history we had studied, right? Using two stones, by sparkling them, or they are going to just scratching them, they are able to produce fire, right? In the same combination, when the combination of two charged particles, there is some energy existed. That energy comes out in the form of light. That is what we are able to visible. Clear? So the working principle of LED is simple. It consists of a P-type and N-type. The material should be forward biased. The material should be forward biased. When we are applying the voltage, the charged particles, especially the electrons from the conduction band, will move towards the valence band, and the recombination occurs. Due to the recombination, there will be an energy existed, or energy comes out. That energy will be nothing but light. Clear? So now I will show the animation. Once again, one. Oh, it's an animation showing that it can't reach this page. Okay, sorry. I think YouTube has been. Yes, I think YouTube has been blocked here. Okay, I will show it later if possible in the laptop. So then in the animation, we are able to see how the recombination occurs and the light is glowing. How the recombination occurs and the light is glowing. Okay. So in the next one, applications of LED diodes. Next one, the application of LED diodes. So it is used for TV backlighting. So people are seeing the TV, right? LED TVs, right now it's more demand in the market. But in the LED light, you are able to get a strip of backlight only concept. What I am trying to mention here is, if you are having a TV like this, it might not consist of a series of LEDs. It should not have like that. Okay. A dots per inch value of LEDs are not connected. Keep it in mind. It is not existing. What is the thing is, a LED light concept is behind these borders. Okay. That will exist on the principle of the already existing or the phenomena. They are existing from LCD technology or some other phenomena they are using, means this backlight method will be projecting and that light will be emitting in the screen. Here, if you open a TV or a LED TV in the mechanical shop or some other service station, you are able to find how the process is happening. Here, next used in displays I mentioned here is mobiles, because nowadays most of the mobiles are LED panels, and the LED panels advantage is power consumption is low when comparing to the LCD. Power consumption is very low when comparing to the LCD. Next used in automotive I mentioned here is in the cars or in the motorbike itself, in the display panel, that is the speed and the timing or the rotations per minute, all those things, or the rotation per minute, all the things displayed over there are represented by means of the digital concept now. So digital concept, they want some illumination, right? They want some illumination. There also these people are using this LED lights. So LEDs are used in the dimming of lights. What is the meaning? So nowadays the government is enacting some other laws that during the daytime also you should have the the headlight should be glowing. So if it is already existing, the major headlight means it will be creating some distraction or interference in the opposite person coming in the opposite side, right? So in the daytime they are just indicating by means of some LED strips. Clear? These are some of the applications I am mentioning here. So LED, most probably they will be getting question around the theory point of view. Most probably they will get the question around the theoretical point of view. Clear? So here we are going to deal with the two gate questions. whether the concept dealing with the LEDs. Just note it down. Red, green, blue light emitting diodes were fabricated using PN junction of 3 different inorganic semiconductors having different band gaps. Sorry, that is band gaps. Okay. The built-in voltages of red, green, and blue diodes are VR, VG, and VS, or VB, VR, VG, and VB. Built-in voltages respectively. Assume the donor acceptor doping to be the same, Na and Nd respectively, in the P and N sides of all the 3 diodes. Which of the following relationship about the built-in voltage is true? About the built-in voltage is true. It depends upon the previous class, what I had mentioned. What they are asking is, they are providing 3 types of LED, but the color is red, green, and blue. Okay, we can mention this as D. Clear? Oh, red, green, and blue. So the question is, how this built-in voltage will be varied? Which one is having less or which one is having more? So we are able to find it. Do you have any options in mind? Do you have any options in mind? Means you can notify in the chat box. Either A, B, C, D, whatever may be. Just a random guess, because already you studied. It's not upon the LED concept what we had studied today. It depends upon what we had studied in the extrinsic and intrinsic semiconductors. Please type it in the chat box. Which choice you prefer, A, B, C, or D? Any guess? No. Here we are going to deal with the energy existing, that is E is equal to H means that concept. First we are considering about the wavelength with GR, right? So the wavelength of red is less when comparing to that of blue. So the wavelength of red is greater when comparing to that of blue. So the wavelength of red is greater than the wavelength of green, which is greater than the wavelength of blue. Okay. We know that the energy band gap is inversely proportional to lambda. Energy band gap is inversely proportional to lambda. So that Eg, energy band gap of red, is very much less when compared to that of energy band gap of blue. So with respect to that, we know energy band gap is proportional to voltage, built-in voltage. Both the values are electron volt only, right? So Eg is proportional to volt. So that we are defining that VR is less than Vg is less than Vb. This is the answer. Right, clear? The answer is B. What they are mentioning is, first we are taking into account the wavelength. Okay, so the depending upon wavelength, the red wavelength is very with GR concept. The rainbow color, the with GR concept, the electromagnetic spectrum, you know that the wavelength of red is great when compared to that of blue. So the next one is Eg is proportional to 1 by lambda. So depending upon the energy band gap value. So this problem or this equation I mentioned earlier in the class, that is the previous session. So depending upon that, Eg is proportional to 1 by lambda or inversely proportional to lambda. So that EgR is less than EgG less than EgB, depending upon the energy gap. We know that energy gap is directly proportional to voltage. So VR is less than Vg less than Vb. Clear one? Next is also, it depends upon the analytical purpose. It is not a mathematical problem. The question is, find the correct match between group 1 and group 2. In the left, group 1 having varactor diode, pin diode, Zener diode, and this Schottky diode. In the group 2, we are having the parameters or some properties, we can say. Okay, voltage reference, high frequency switch, tuned circuit, current controlled alternator. Please guys, give me the answer quickly. Guys, because these are the basic things we covered earlier. Diode, the types of diode, and you would have studied the same in the electron devices. What are the applications of diodes, different types of diodes? Any guess? You can type, it's not a problem. Use the chat window, just type. No. Nobody is guessing. Okay. So what is that is, let me start with the Zener diode. Zener diode, if you come with the term Zener diode, the first thing will be considered as the avalanche breakdown. The first thing will come to our mind is avalanche breakdown. Then they happen the Zener breakdown due to the voltage condition. What is the breakdown occurs at that particular voltage? The breakdown happened. So we are studying it, the avalanche breakdown. So we are able to control the voltage. We are able to control the voltage. The application of Zener diode is voltage regulator. The application of Zener diode is voltage regulator. So here with respect to that, we are having only the voltage reference value. We are having only the voltage reference value. And the next one, I can say it as this varactor diode. What is that? Varactor diode. So in the varactor diode, we are having the variable capacitor concept. If you are having a tuned circuit, we will be having like this. Please. Please adjust with the inductor, okay? Consider the opposite as an inductor. Even though I can't accept that, but please. Then we are having some capacitor. This is the tuned capacitor. Sorry, this is a tank circuit or tuned circuit, what you will have. If you want to maintain a constant frequency, this is more than enough. If you want to maintain a constant frequency, it is more than enough. But if you want to change a variable frequency, in the case of variable capacitor, we can use the varactor diode. They can use the varactor diode. So the varactor diode is used for the tuned circuits. Varactor diode is used for the tuned circuits, right? Next is the Schottky diode. Schottky diode. Their threshold voltage is 0.25. What is that? 0.25. The 0.25 voltage is very much less when comparing to that of silicon. Silicon, that is 0.7. Germanium, that is 0.4. So this Schottky diode can be act as a switch which is high sensitive. The switch is high sensitive. So here we can choose the option high frequency switching. Here we can choose the option high frequency switching, Schottky diode. Next, the pin diode. The pin diode, you know that their application or the concept behind that we are using is a current controlled alternator. The pin diode we are using here is used in the concept of current controlled alternator. So this is the concept or the parameters. This kind of a question you can expect. So it covers all the 4 varieties of diodes. So you should cover all the syllabus or concepts, right? So Zener diode, which deals with the voltage regulation. Voltage regulation. You know the avalanche breakdown concept. So depend upon that, the voltage can be maintained. So that Zener diode is related with voltage reference. And the next one, varactor diode, is dealing with the tuned circuit. What is the tuned circuit? That is variable capacitor mode. That is variable capacitor mode. Then the pin diode that deals with the current controlled alternator. Current controlled alternator. The Schottky diode is nothing but high switching frequency. High switching frequency because the threshold voltage is very much less when comparing to the germanium and silicon mode. So E, the answer is 3. So the option is C. Clear? If you want to note it down, just note it down because it might be useful for some other way. In any other questions, we can't expect the same question or same pattern, but we can use the same concept in different areas. Yeah. So the LED or the different diodes covering that area, I come across with the concept and some two problems. Okay. So next one is PN junction diode. Next one is PN junction photodiode. Sorry. What is a photodiode? What do you mean by photodiode? Good. C. Augustine Kumar. Can I get some answer? Photodiode. Hello friends, it might be a 3-hour session. If it is not interactive or responsive, then it will be going to be very boring session. If one side talk means it is going to be a boring session. Please interact with me. It might be wrong, it might be a blender mistake, don't bother about that. Just give some time to type or use your mic to say something. Okay. It converts optical to electrical signal, light into current. Yes. So both the concept of the dealt with photodiode. Photo is light, right? Photo is light. So diode you have two junctions. Diode you have two junctions. The PN junction photodiode is going to convert the light energy into electrical energy, depend upon the current or voltage. So the photodiode is one type of light detector used to convert light into current or voltage based on the mode of operation of the device. The photodiode is one type of light detector used to convert the light into current or voltage based on the mode of operation of the device. Clear? So next, comprises of optical filters, built-in lenses, and also surface. What I mentioned here is optical filters, built-in lenses, and also surface areas. What I mentioned here is, if you are using a photo detector for in the sense of electroluminescence or fluorescence concept, we are using the photo detector in the electroluminescence or fluorescence concept. The fluorescence is an excitation, a photon excitation. Okay, if you are having a charged particle like this, okay, and if you are going to have some excitation, you are going to have some excitation that, for example, a light is incident on it. Light, some external light is incident on it. So this light is going to generate some first color. It is going to generate some first color. That pattern can be used for different applications. For example, in the PCR test kit, no. Nowadays it is very familiar around most of the people, not only technical people or medical people. The PCR test kit is now become due to the corona issue. They are giving some strip. The strip consists of some reagent. Okay, the strip consists of some reagent. In that strip, they are placing the blood sample of that particular person or the patient who you want to diagnose it. Okay, you want to test it or diagnose it. That particular patient's blood sample is going to be placed in the particular strip. That strip will be placed to some excitation process. That reagent is mixed with the blood sample and that will produce some color excitation. That will produce some color excitation. That color will be observed. That color will be observed and able to give the result like whether this particular person is having this parameter, that is COVID-19 positive or negative. So here they are using optical filters, built-in lenses to magnify, and also it consists of the surface area. The area should be having a defined pattern. The area should be having some defined pattern. Okay. The photodiode is one such diode that used to convert light into current or voltage based on the mode of the operation. The second point I dealt with the concept of the operation principles. So it comprises of the variable parameter, that is optical filters, to select the particular band, what color you want to send. Next, in the built-in lenses to magnify the quality of that color exciter. Okay, and also the surface areas. Clear? Next, these diodes have a slow response time when the surface area of the photodiode increases. Yes. If you increase the pattern where you want to excite, area is increasing, the response or the excitation of that energy coming outside, the excitation of energy coming outside will be time taken. But if you decrease the area or decrease the size, it is going to be very regenerative. This might be points you can expect in the analytical point of questions in the gate. Okay. Are like regular semiconductor diodes, but they may have either visible to let light reach the delicate part of the device. The difference is it is the same PN junction diode. It is the same PN junction diode, but this concept deals with where that particular light should reach, where that particular light should reach, and what it should be the concept you want to deal with. Okay. So the next one, here we are going to deal with the cross-sectional area or the schematic block diagram. What else you can say? Okay, the cross-sectional area or the schematic block diagram of a PN junction diode. Clear? The PN junction photodiode consists of a P-type material here. Okay, the P-type material is this. What I can say, a purple color. This purple color is nothing but the P-type substrate. Clear? All the remaining areas we are having a N-type substrate. This P-type substrate comes out with an electrode, anode or cathode electrode that is coming outside. That is combined in the negative terminal. That is combined or joined in the negative terminal. Keep it in mind. The major difference between LED and photodiode is this. In LED, forward bias is happening, but in photodiode, the reverse bias process is happening. The P-type is connected in the negative side and the N-type is connected in the positive side. The P-type is connected in the negative side and the N-type is connected in the positive side. Clear? Okay. So the silicon oxide. So these are the things we are going to study in the IC processing. Okay. Oxidation purpose, we are using the silicon oxide. This will be act as a dielectric between this particular electrode and the substrate. This particular electrode and the substrate. And this we are having a electrode from the N-type material. They are having an N-type material. Okay, so this is the cross-sectional area. We are going to visible what is happening inside the photodiode. What is happening inside the photodiode. Here we are going to combine, or we are not going to recombine. We are going to separate a recombined pair. We are going to separate a recombined pair. You are able to see holes are moving in one direction and electrons are moving in another direction. So when the light incident on the recombined charge particle, that charge particle will separate or segregate themselves into different areas. Okay. So the first one is the schematic diagram of reverse biased PN junction photodiode. So keep it in mind, the photodiode is reverse biased. Okay. Next one is the depletion region. So ND and NA are the donor and acceptor concentration in the P and N sites. ND and NA are the donor and acceptor concentration in the P and N sites. Next to the field in the depletion region. Third graph is representing that field if the electron concentration will be in the negative side for the reverse bias. Okay. After that only it is going to be increased and get the saturated. Okay. So once you are increasing, it depends upon this concentration, this positive donors, this value of electric field is going to be decreased first, and then it is going to be increased in the negative resistance value only. The negative resistance value only. So this is the schematic diagram, and the second one is the addition of positive donors and the negative acceptors. So depend upon that, what is happening in the electric field will be depicted in the third diagram. Yeah. So in the next working principle, when a photon of ample energy strikes the diode, okay, we are having a couple of electron hole. This mechanism is called photoelectric effect. When a photon of ample energy strikes the diode, we are going to generate an electron separately and hole separately. Okay, the carriers are removed from the junction by inbuilt electric field. Therefore, the holes in the region move towards the anode. The holes in the region move towards the anode, and the electrons move towards the cathode. So, guys, keep it in mind. The major difference is nothing but in the photodiode, we are dealing with the reverse bias condition. Keep it in mind. LED, we are dealing with the positive for forward bias condition. Clear? So in the forward bias condition, we are dealing with, we are able to combine electrons and holes. We are going to combine electrons and holes. That is recombination occur. In the reverse bias, we are going to separate. We are going to separate holes and electrons. This is the major difference. Okay. So this diagram, the first one, we are reverse biasing the photo generation. That is, the light is generated in the space charge limit. This yellow area is nothing but the space charge limit that generates the electron and hole. That generates the electron and hole. Okay. So both fall their respective energy hills. Hills are nothing but we are representing like this curve edges. Hills manner we are representing here the curve edges. These are, we call it as hills. Okay. So the IPH is representing the photo current. IPH is representing the photo current. The conventional current that is moving from positive to negative side. The positive to negative side is representing here as photo current. Clear, ma? So, in the reverse bias condition, photo generation occurs. The photo generation occurs in the space charge limit. That is the name given in the photodiode region. That is yellow region. That is the boundary gap between that P-type and N-type material. That is the combined area. Usually, we can say it as a junction. Okay, in that combined area, we are able to separate. That concept you should understand. That is, separate electrons separately and holes separately. Clear? So that movement, due to the charge particles movement, we are able to get current. We are able to get a photo current. Next one, due to the photo current, we are applying the diffusion concept. We are applying the diffusion concept in the neutral region. This is the SCL region, that is the space charge limit. Next, we are going to the neutral region. Here, due to the diffusion concept, we are bombarded with the light energy. The holes are moving towards that whole area, that is N-type, and the electrons are moving towards the P-type. You are able to see here, right? So that only we are able to get some other photo current. The major difference between these two diagrams are, here we are dealing with only the junction. And here we are going to deal with the neutral area by means of some external force, how these things are happening. So external energy is bombarded here. From the pair, you are able to separate the hole. From the pair, you are able to separate the hole, and the separate the electrons will be moving to the other direction. Clear? Next, here we want to deal with the two concepts only: short circuit PN junction photodiode. One is short circuit and another one is open circuit, because we will deal with the problems in the gate mostly on this area. Okay. So in the short circuit, there will be no source. But due to the bombardment of the external light source, the photo generated, okay, electron and hole in the SCL will roll around the hills, because there will be no external things. But due to the light bombardment, the separation of electrons and holes will be moving from the longer area to a steeper area by means of the slope. Okay. Next, to open circuit, we are having the separate one more value, that is iron diode, that is diode current. So here, the PN junction is open. Electron flow, the energy is drift, but there is a voltage open across the diode that causes them to diffuse back. That is, you are able to see here the blue lights. No, first it is moving from the top to bottom. Then due to the reverse voltage, it is moving from the bottom to top. This is happening during the open circuit process. If the holes are moving from the steepy hills from top to bottom due to drift, in the same reverse process due to the bombardment and the electrical energy applied over that, that is moving from here to the other side. So IPH that is moving in the left side, and I diode that is moving in the right side. Keep it in mind that photon current will be moving from positive to negative, and the diode current will move in the negative side. That is the reverse direction. Clear? So this is the one thing we will come across. So here also I am not sure whether it will be play or not. So I will play later. Okay. This is also the animation. It is not playing. So we are going to the photodiode application. So this is the photo detectors. This is the photodetectors, that is the light detector. We are going to have some strip, the silicon strip in the top edge, which is going to receive the light. It is going to receive the light. Okay. So then the image sensors also we are using the photodiode concept. So image capturing charge coupled device also we are using this same concept. Clear? Do you have any doubts? So next we are going to deal with the problems. Okay, note it down. In the forward bias photodiode with increase in incident light intensity, the diode current whether increases, remains constant, decreases or remains constant, but the voltage drop across the diode increases. So these are the choices. The question is in a forward biased photodiode. Photodiode usually working reverse biased forward biased photodiode with increase in incident light intensity. With increase in incident, sorry, what the diode current. It is not the photo current, it is diode current. What will happen? Can I get any answer? C. Decreases. Keep it in mind in the forward biased photodiode. Okay, let it be. With increase in incident light intensity, that is a parameter they are provided. The diode current, they are not bothered about the photo current. Sir? How much, sir? How much? That's great. Okay. Augustine Jabakumar C. Only one answer. So I will show it. The photodiode light is coming outside. Already I mentioned that a reverse current. Okay, the diode current and the reverse current that deals with proportional to elements. So if you are having, what is it? Reverse current is nothing but here they are mentioning is photo current. Okay, ma'am? Reverse current is photo current. So depend upon the illuminance, it is going to be, reverse current is also going to be increases. So the increase in incident light intensity, that current is also going to be increases. Because the graph is like that. The current, the illuminance, depend upon the illuminance value, that going to be increases. Note the point I mentioned right here, the forward bias. Because the photodiode concept will be working in the time of, at what time? Reverse bias condition. Photo concept. Okay. So now in the forward bias condition, it is working on in the same concept of PN junction diode. So the light intensity will be increasing, the diode current is going to be the forward bias condition. So it is going to be increasing. It is going to be increasing. Clear, Augustine? So that's the answer is going to be increases. Okay. The next one, yeah, it's a fantastic question. It's also on the analytical part. Choose the proper substitute of X and Y to make the following statement correct. Okay. So tunnel diode and avalanche photodiode are operated in X bias and Y bias respectively. Simple question. In which biasing condition tunnel diode and avalanche photodiode will operate? Okay. So in the X, you want to replace with either forward or reverse. In the same way, Y also you replace the same with forward or reverse. Can I get any answer? Here the answer I mentioned, photodiode. We will just skip the tunnel diode, photodiode. Photodiode should operate in reverse condition. So you can skip these two answers. Okay, you can skip these two answers. The remaining two are here. Can I get any answer between A and C? Nishorni, C. Yes. Tunnel diode, good one. The tunnel diode, it works in the forward bias condition. The avalanche diode that works in, that is avalanche photodiode that is works in the condition of reverse bias condition. That is a photodiode. The tunnel diode, the other things you can mention, high speed switch. It is a high speed switch. It operates very fast in the microwave frequency region. Okay. The avalanche photodiode is works on the principle of avalanche breakdown. Avalanche breakdown concept. So it undergo breakdown at the specific reverse voltage to prevent the damage. So in certain areas, if you are having a fluctuation and the reverse voltage is increasing beyond the limit, we can use that avalanche photodiode or this type of concept to rectify the process. Okay. So here it is used in the microwave oscillators and amplifiers. It is most negative conductance device. It is mostly a negative conductance device. Why it is? The tunnel diode principle will be like this only. Okay, it will be increasing, then decreasing, then once again increasing. Okay, ma? The tunnel diode concept will be like this only. So in this region, they are having a negative temperature or negative resistance value. So it most acts as a negative conductance device. Okay. So depend upon these things, the principle, the reverse of the conductance, the reverse of the resistance will be happening, and that tunnel diode can be worked in the principle of or worked in the process of that negative conductance device. These points are important, note it down, because this particular question is asked with respect to biasing. Okay, they can ask with respect to negative conductance device, positive conductance device, or a negative microwave frequency or some other frequency they will ask. So there might be different type of questions. There might be different type of questions you can expect from just a tunnel diode and avalanche photodiode. I think you note it down, right? Next question. At 300 Kelvin, what is that? At 300 Kelvin, the band gap and the intrinsic carrier concentration of gallium arsenide are 1.42 electron volt and 10 to the power 6 per centimeter cube respectively. Okay. In order to generate electron hole pairs in gallium arsenide, which one of the wavelength ranges of incident radiation is most suitable, provided Planck's constant, velocity of light, and charge of electron? So what are they provided? Provide a given value, we can write it down. P is equal to 300 Kelvin, and the energy band gap of the intrinsic carrier concentration 1.42 electron volt, and the carrier concentration is 10 power 16. Okay, 10 power 16 per centimeter cube. In order to generate electron hole pairs of gallium arsenide, what should be the wavelength range? Any idea, guys? So you know that E is equal to h nu, the basic formula, right? The Planck's constant formula, E is equal to h nu, the photo energy. The h is the Planck's constant, dot nu is nothing but frequency. The frequency formula is C by lambda. We can write it as C by lambda. The provided value is 6.626 into 10 power minus 34 for h. And C is equal to 3 into 10 to the power 10 centimeter per second. Clear? So E photon is equal to 1.24 micrometer by lambda. When we are substituting this value, you can use the calculator and check it out. 1.24 micrometer by lambda. To get the energy, that is that, what is that? To get that wavelength of where we are going to apply this concept and how this concept is working in phi. So E photon is greater than or equal to Eg. E photon should be greater than or equal to Eg. Why? In the photodiode, let it be a photodiode, but the question I mentioned that is much needed. I put that for gallium arsenide, right? Please note it down, guys. Gallium arsenide is a material that is used for the photodiode concept. So they didn't mention anywhere about the photodiode. They didn't mention nothing about the photodiode. Is there anyone mentioned about that? No. But this concept or deal with only the photon energy. So gallium oxide material, if they are mentioned in the question paper, you should think about the concept of photodiode. Okay, ma? Okay. So the photodiode, so this is considered some material, and if you are going to travel, energy band gap is here, right? You have some energy band gap. This is the valence band V. If this is the conduction band. If the electron should move from this particular region to conduction band, then only all the things will happen, right? Valence band to conduction band. So the photon energy should be greater than band gap. We should have the question, why this photon energy should be greater than or equal to band gap? This is the answer. The photon energy should be greater than or equal to band gap, so that only we are able to move the electron from the valence band to conduction band, so that we are able to produce the photon energy. Okay, light energy. Clear? So 1 point V photon, we already find that 1.24 divided by lambda, we should be greater than or equal to 1.42, because we got the value energy band gap. E is equal to 1.42 electron volt. So by substituting or by using the mathematical concept, if you reverse it, lambda by 1.24, the greater than or equal to will be changed to less than or equal to. Okay, so 1 by 1.42. So lambda less than or equal to 1.24 micrometer divided by 1.42, which is equal to 0.87 micrometer, which is equal to 0.87 micrometer. Clear? 0.87 micrometer. So the answer will be less than or equal to, right? 0.42 micrometer to 0.87 micrometer. This will be the answer. Okay. Can I give one more question here? Note it down. At T is equal to, you are going to give the answer. Students, you are going to give the answer. Note it down. At T is equal to 300 Kelvin, the band gap of intrinsic carrier concentration of same gallium arsenide, let it be. Okay. Is going to be 1.3 electron volt. 1.3 electron volt. And 10 power 6 per centimeter cube. 10 power 6 per centimeter cube. In order to generate electron hole pair, which one of the wavelength range? Which one of the wavelength range you should going to find? Okay, going to be most suitable. 1.3 electron volt. Give me the answer. 1.3 electron volt. That is the only changed value. All the values are remaining same. 1.3 electron volt. Can I get the answer? Formula is here. What is the answer, ma'am? Did you understand my question? At 300 Kelvin, the band gap and the intrinsic concentration of gallium arsenide are 1.3 electron volt. Okay, and 10 power 6 per centimeter cube respectively. So, in order to get the whole per gallium arsenide, which one of the wavelength we should be applied? This is the concept. Augustine Jabukwa. You to get the answer? 0.3 lambda to 0.95, okay, micrometer. Micrometer. Nisharni, is that 0.95 micrometer? 0.95 micrometer. Okay, fine. This 0.3, okay, let it be. We can change or we can use some other value. Depends upon that. But the value should be in the range of 0.95 micrometer. Good. That's the answer. Yeah. Next question. I had given the answer already, but it is very simple logic question. When the optical power incident on a photodiode is 10 microwatt, optical power, okay, and the responsivity is 0.8 ampere per watt, 0.8 ampere per watt. The photo current generated in microampere, that is the question. It's no need about the problems formula, not like that. Just use the logic, give me the answer. Good. Augustine Jamkumar 0.95 micrometer, that is also fine. Good guys. I have already given the answer, 8. How it will be coming? We consider like optical power, okay, incident, optical power incident, okay. So you are having some power, that unit is going to be watt, and you are having some responsivity, that is ampere per watt. If you multiply these two values, you will get some ampere value. Don't bother about micro, okay, you'll get some ampere value. That is what required. Photocurrent generated in microampere. That's what I said. Without any formula, you can use the logical concept, you will get the answer. Responsivity is equal to 0.8. There is two more questions. Okay, 0.8 ampere per watt divided by power incident is equal to 10 microwatt. Photocurrent is equal to power incident into responsivity is equal to 8 microampere. Clear? So the optical power incident on a photodiode is 10 microwatt, and the responsivity. Usually we will skip this problem, even though if I had gone for the exam means I might not think with the logical things. I thought that I don't know the formula for photocurrent, what can I do? Then I will skip. But the logic is simply here. Okay. Guys, is there any doubt in photodiode or LED? Now I am moving to the solar cell. That is the next concept or next advancements of that. What I can say, photodiode concepts advancement, the application, what we are having in the photovoltaic cell, solar panel, right? That is what we are going to deal with. Can I continue? Is there a doubt or can I continue? Okay. The solar cell or photovoltaic cell is an electric device that converts energy into electricity. Energy likely into electricity by photovoltaic effect, okay, by physical or chemical phenomena. So the three basic attributes are there. One is the absorption of light, generates either electron hole pairs, the separation of charge carriers of opposite type, the second attribute, the separate extraction of those carriers on external circuit. So these three are the major components of this solar cell. So the operation of photovoltaic cell deals with the three parameters. That is, first one is the absorption of light, generating either electron hole pair or excitons, and the second one is the separation of charge carriers. So we should separate the positive side and the negative side separately from the solar panels. Clear? So that will be taken outside in the external circuit. That can be used as the movement of charge carriers. With that movement of charge carriers, we are able to produce the current. Okay. So this is the pictorial representation or symbol of solar cell. Okay, this is the pictorial representation or symbol of solar cell. Okay, this is the symbol, not cross-sectional, a symbol, schematic diagram or the cross-sectional view of the solar cell. So this is the P substrate. What is the P substrate? This area, this larger area is the P substrate. Okay, ma'am. and that substrate is layered with N-type material. That substrate is layered with N-type material. And above that, we are having this, what is that? As anti-reflection coatings. We are having this anti-reflection coatings. So here we are having a back contact that is also a substrate of material contact. Okay, this back contact is nothing but a material contact. So what is happening is when the light is incident out here, these electrons and holes are directly combined. These gaps are necessary. These gaps are necessary so that they will directly come to the PN junction. They will directly come to the PN junction, where that is the separation of positive charge particles and negative charge particles will happen, and from that we are able to generate the current. From that we are able to generate the current. This two-dimensional representation is converted to three-dimension in this diagram. Guys, understood? So this is the solar cell diagram, and in this diagram we are able to see the two-dimensional representation. The P substrate is overlaid with an N substrate layer, and above that we are having a anti-reflection coating, and anti-reflection coating intermediate we are having the substrate A conducting material. So when the light is passed over that, depending upon the dimensional quantity of anti-reflection coating, it will come directly to the PN junction. It will come directly to the PN junction. From there, they are going to be separated. From there, they are going to be separated. Clear? Representation of the solar cell having the two-dimensional pictorial representation what we are having here. So it's having a P substrate and layered with an N substrate, and other than we are having the anti-reflection coating. Anti-reflection coating is the one layer which is going to allow the photons to directly come to the NP junction. So this graph, this is very, very important with respect to the solar cell. Clear? So usually this black line, I'm not sure whether you are able to see this line. Okay, this black line is the process that is happening in the solar cell for a neutral, forward and negative bias condition. Okay, so in this forward and reverse bias condition, we are having some dark current. I am mentioning some dark current without applying some voltage or some current. We are having some value of current. That is the representation. Okay, the dark current is nothing but without having the external source of voltage, we are having some value of current over there. Clear? So in the next diagram, this particular thing is occurred due to the process of two things. One is open circuit voltage and another one is short circuit current. One is the open circuit voltage and the short circuit current. If you are further increasing, the voltage, that is the diode voltage, so depending upon the incident photon, this is representing ID, the current, and VD, the voltage. This is IL. Here we are using that IL as the source of illuminance. The source of luminance. Okay. So here we are not representing by any other terms. We are using a current source that is representing the source of. Then we are having the diode, and after that we are having this circular ID and the VD value. So in this graph, this particular region is going to represent the fill factor. So in the A type of questions, you are expecting some one or two questions with respect to the fill factor concept. Fill factor concept is nothing but at a certain area, how you are able to fill that particular N type or P type substrate. For example, the solar panel is for 10 to 10, that is 100 square feet area. 10 feet, 10 feet, 100 square feet area means how optimized you can get by the intervention of less in a spacing, you should get more energy. Less space, you should have the more energy. So this fill factor is creating a major impact with respect to the solar panel, that is photovoltaic cell implementation. So depending upon this last circuit, this IL, we are going to convert that into the circuit diagram, and we are having an equation like ID is equal to I naught into e to the power of VD divided by VT minus 1 minus IL. Okay. VOC, that is open circuit voltage, is equal to VD divided by that ID is equal to 0. VD at ID is equal to 0. So 0 is equal to I naught into e to the power of V open circuit divided by VT minus 1 minus I. O0 is equal to I naught into e to the power of V open circuit divided by VT minus 1 minus I. So we are able to get the values like V open circuit is equal to Vt ln of IL divided by IO plus 1. Vt ln of IL divided by IO plus 1. Clear? We got the value, right? So this equation, open circuit voltage equation, is important for problem solving. Next, the short circuit current ISC is nothing but minus IL. At that condition, Vd is equal to 0. Vd is equal to 0. The value is going to be e to the power of 0 minus 1. E to the power of 0, you know, 1. 1 minus 1 is 0. So the value Id is equal to minus IL, which is nothing but ISC. At Vd is equal to 0, we are assuming that it is ISC. So just copy it down, because the problems coming from the solar cell or the special diodes will be coming from this area only. Because already we discussed with only the analytical part and the theoretical part questions. Clear? So now we are moving to the now we are going to see the working principle. So this is the conduction band, that red color, and the green color, that is the valence band. So the carrier, the Fermi level carrier concentration is represented by the blue color. Okay. When the photon or light is incident on there, we are going to generate a carrier generation, that is positive and negative charge separately. So electron should be moved towards the N type, and the proton should be moved towards the positive type. This is the diagram is representing. Clear? Here we are using some photon. That energy is injected on the Fermi level. That Fermi level, we are having an electron hole pair that will be separated, and that will be moved with respect to the types. That is N type. ET is moving to N type, and PH or holes are moving to the P type. Where that concept is here, the operating diode in the fourth quadrant generates power. This is the major thing. The operating diode in the fourth quadrant, this particular area, is only used for generating power, photovoltaic cell. Okay. If we are using the same in this area, that is third quadrant, means that will be working as a photo detector. Already we have studied the application, right? The third quadrant we are using means we are using it as a photo detector, and this area is the solar, converted into solar cell. This region, this red region I marked, no, this will be specifically for the fill factor. I reverse it, okay? That region I reverse it like a parabolic structure. So here on the left side on the x-axis, we are having the open circuit voltage, and the y-axis I'm having the short circuit current. So I want to find the fill factor value with respect to that of, this is the point, with respect to that of the peak voltage, that is the maximum V value and maximum I value. So the power maximum is equal to Vm into Im. But the fill factor formula, we can give it as Vm Im divided by Voc into Isc. Vm Im divided by Voc into Isc, which should be less than 1. It should be less than 1. This should be necessary for the efficiency of the solar panel. For example, if you go to some of the shops, you want to implement a solar panel in your top, that is house top or some of the building tops, post or whatever may be, they will ask for the quotation. And that depend upon the panel, they will be have different efficiency. Depend upon the efficiency and the life of that particular solar panel, the rate might be clear. So depending on that characteristic or that parameters, we are dealing with that fill factor. Okay. So the efficiency is equal to Vm Im divided by P. That is equal to fill factor into Voc Isc divided by P, because we don't know the maximum value as well. But we know the open circuit voltage and the short circuit current. Clear? So here in these two areas only we are going to see the problems. We are going to deal with the problems in the gauge. Okay, guys. Next, the type is Schottky barrier cell. One is Schottky barrier cell. The operation is similar to that of the PN junction, but the conducting grid is on the top of metal layer. That is a major difference. The conducting grid is at the top of the metal layer, but the problem is it is surface damage due to high temperature. The surface will be damaged due to high temperature. And the next one is grooved junctions. That's what I forgot in the starting. That is during the presentation in this lecture we are going to see, and said no. I forgot of the grooved junctions. So this is the representation. Here we are having the N-type silicon, and this is the P-type substrate. Okay, this layer is there. That uneven line is here, right? This is nothing but the PN junction. So when the light is incident, that light will be passing over to the PN junction. From there, the holes and electrons. You are able to see, no, the holes and electrons are separated, and we are able to get the conduction. The higher PN junction area and higher efficiency. So the solar panels, you are able to see the strips. Solar panel, you are able to get the strips. The strips reason are if the region is designed in such a way so that only the light will pass over the junction, and due to the junction, the electrons and the holes will be separated, and that separated current will be able to generate the power. Okay. So now we are going to deal with the problems. Note it down. For a particular intensity of incident light on a silicon PN junction solar cell, the photocurrent density JL. Okay, the photocurrent density JL is 2.5 milliampere per centimeter square, and the open circuit voltage is 0.451 volt. 0.451 volt. Consider thermal voltage VT to be 25 millivolt. If the intensity of the incident light is increased by 20 times, so first the condition is having a stable one. Next, the intensity of incident light is increased by 20 times. Assuming that the temperature remains unchanged, find the open circuit voltage. So it is a PN junction solar cell. It is a PN junction solar cell. The photocurrent density is 2.5 milliampere per centimeter square, and the open circuit voltage is 0.451 volt. Consider the thermal voltage VT is to be 25 millivolt. So how can I solve this? So here I am using first the preliminary condition. JL is equal to 2.5 milliampere per centimeter square. VOC is equal to 0.451 volt. VT is equal to 25 millivolt. Open circuit voltage formula we already derived. What is that? VT ln of IL by I0 plus 1. But we can assume that IL by I0 value is very much greater than 1. IL by I0 value is very much greater than 1. So I can take it as VOC is equal to VT ln of IL by I0, which is equal to 0.451 volt. 0.451 volt. Next condition is the same system is increased to the intensity of light by 20 times. Intensity of light by 20 times. So VOC is equal to VT ln of IL1 by IO. I am substituting IL1 is equal to 20 IL. So the ln of AB is equal to ln A plus ln B. Due to that formula, VOC1 is equal to VT ln of 20 plus VT ln of IL by I0, which is equal to 0.07489 plus 0.451. VOC1 is equal to 0.5258 volt. 0.5258 volt. Clear? Here the value is because the system that your solar panel is same. Okay. First time go to the light of intensity of light is some X, and after that I am induced some intensity of light by 20 times. Increase the light by 20 times. So more intensity of light is coming. So the question is open circuit voltage, whether it will be increasing or decreasing. It is increasing. So 0.451 volt to 0.5258. It is indirectly meaning that if you are having a solar panel in the top, in the afternoon time, you are able to get more current when compared to the morning and evening due to the shade, right? So that is the concept. So if you are having more light intensity, the open circuit voltage will be more. From that open circuit voltage, you are able to get the current for the house or that particular application. Clear? Did you finish? Did you finish? Okay. Note it down. The same problem with different values. P and junction solar, the photo current is The photo current is same 2.5 milliampere per centimeter square. The open circuit voltage is 0.5 volt. The open circuit voltage is 0.5 volt. And consider the thermal voltage Vt is equal to thermal voltage entry is equal to 26 millivolt. 26 millivolt. And the intensity is increased by 10 times. Then what will be the VOC value for this open circuit voltage? Can I get the answer quickly? The current open circuit voltage is 0.5 volt. Okay, if the intensity is increased by 10 times. Be quick one, give me the answer. Guys, give me the answer, guys. Surely 0.5598. I am getting the value of 0.5589. Okay. Okay, ma'am. What is the answer? I think so. I'm also randomly giving the things. Someone cross check it. Can I get some other answer? It is volt. Okay. We should mention the unit also. Next question is a solar cell of area 1 centimeter squared operating at 1 sun intensity. These are some of the words to confuse us. Okay, there is no such a deviation. Has a short circuit current of 20 milliampere and open circuit voltage of 0.65 volt. Assuming room temperature operation, thermal equivalent voltage of 26 millivolt, the open circuit voltage at 0.2 sun intensities. Their question is open circuit voltage. Okay. So the value is they are considering as sun intensity with the rate that already we are saying that the intensity. That is the same X. But it has to be sun intensity is reduced to 0.2. Okay. That is the 80% of the sun intensity has been reduced. Already we are having that voltage intensity depending on the previous problem. We are having that increased by 20 times. Clear? Here it is indirectly saying that 1 sun intensity and it is 0.2 sun intensity. So it is going to be decreased. So what will be the answer? The value given is sun intensity is equal to 1, open circuit voltage is equal to 0.65 volt, current due to light incident is equal to IL is equal to 20 milliampere, thermal voltage Vt is equal to 26 milliwatt. What will be the answer, ma? Please give the answer. Please, the same concept. Make it possible. Same concept as the previous problem. 2014 also they asked, and now in 2017 also they asked. So it's because there might be criteria. they will, for individual section, for signals and system, some marks. Electron devices, some mark. Electron devices also special diodes and IC technology, some marks. And for intrinsic and extrinsic semiconductor, some marks. So they are having some calculation like that. So different allocation of marks for different areas. Clear? So you can expect some questions from solar cell or photodiode frequently. Mostly because nowadays they are having set 2 also, not only set 1 question, morning one session and afternoon one session. So they are expecting some set 1 and 2. So we can expect this type of questions in a different way. Did you get the answer? So the sun intensity is equal to 1, VOC is equal to VT ln of IL I0 plus 1. So assumption is IL by I0 is very much greater than 1, so that we can say VOC is equal to VT ln of IL by I0, which is nothing but 0.651. 0.651. So the ILN is reduced, we keep it in mind, 0.2 value. Okay, there the 20% is increased, here reduced. So VT ln of 0.2 is equal to minus 0.0418, minus 0.0148 plus VT ln of IL by IO, which is equal to 0.65 volt. The voltage or this open circuit voltage is 0.608 volt. Open circuit voltage is 0.608 volt. So that if one analytical question they can ask directly. Depend upon, or you note it down and give me the answer. Consider a solar panel of area 10 centimeter square. The solar panel of area 10 centimeter square, having an incident intensity of L1, incident intensity of L1 with the open circuit voltage VOC1, L1 VOC1, and at the same temperature the intensity is increased to L2, and the open circuit voltage is VOC2. Full stop. The desired conditions are VOC1 less than VOC2, VOC1 equal to VOC2, VOC1 greater than VOC2. What will be the answer? First one, VOC1 less than VOC2. Second one, VOC1 is equal to VOC2. Third one, VOC1 is greater than VOC2. Give me the answer. Straight away you can give, right? You are taking this much time. I am saying that the intensity has been increased from L1 to L2, right? And the open circuit voltage also increased from VOC1 to VOC2. That is the answer. So the first choice, VOC1 less than VOC2. That is the answer. Good. Aisha, that is the correct answer. Good. Clear. So you can expect this type of questions also. So depends upon the problems and what you are working out, you are able to come to the conclusions. Okay. This figure shows the IV characteristics of a solar cell illuminated uniformly with a solar light of power 100 milliwatt per centimeter square. Good. The solar cell has an area of 3 centimeters squared and a fill factor of 0.7. The maximum efficiency of the devices. Maximum efficiency of the devices. So here they have provided a graph, okay? The figure IV characteristics solar cell illuminated uniformly with a solar light of 100 milliwatt per centimeter square. Okay, uniform power of 100 milliwatt per centimeter square. The total area is 3 centimeters square. The total area of the solar panel is 3 centimeters square. Okay, the power of injection is 100 milliwatt per centimeter square. And a fill factor is 0.7. So mostly it will be filling. 0.7 means it is going to be mostly. The maximum efficiency what we can form. The fill factor is 0.7. So the maximum efficiency what we can expect. So let me see. The power input is equal to 100 milliwatt per centimeter square. Okay. Area is equal to 3 centimeters square. The fill factor is equal to 0.7. So efficiency, the formula you know, P out by P in. So V max by into I max by P. Okay, usually IS is equal to IM. I will say OA put like that. V max is dot I max divided by P in. So V max dot I max divided by P in, because I had given only VOC and ISC value, right? I had given VOC and ISC value in the graph. From the graph, we are going the VOC and IOC value, so that I had changed the problem or the formula to my convenience. That is V max dot I max divided by P in dot VOC into ISC divided by VOC into ISC. Okay, so now VOC dot ISC divided by P in into V max dot I max divided by VOC into ISC. It is nothing but fill factor. It is nothing but fill factor. Okay, so substituting the values, you are able to get the value 90 into 0.7 divided by 300. 300 is nothing but the total power per area. Okay, milliwatt. So the value is equal to be 21%. The value is going to be 21%. So the form factor is, the form factor is 0.7 and the area having the less power. They are having less intensity. The efficiency is only 21%. If the incident value is more, for example, if we are having more incident, that is 180, this value is going to be more, then we are able to get the better. Clear? The short circuit current ISC 180 milliampere, right? If that is increasing, means you are getting the more efficiency. Clear? So now the special diodes are over. Nowadays, or today we had seen it LED, photodiode, tunnel diode, and now the solar cell. Clear? This is the special diode concept that is given in the GATE syllabus, and these are these type of questions you can expect. Clear? Next, we are moving to the core steps of production of integrated IC. Can anyone give the steps of IC fabrication? Some 3 or 4 steps, important steps of IC fabrication. Some during our the college syllabus, we will study around the 7 or 8 steps, right? 7 or 8 steps. Even Aisha, Agustin, Jamkumar, 4 maybe. Can you give me the steps? That is also important question, right? In LIC, first unit, there are some important steps of the IC fabrication. Most probably you studied the Rai Chaudhary book, right? In integrated circuits. because that is like a Bible for clean integrated circuits. 99% of the people will be follow the same. Can some 2 or 3 steps? Anyone, 1 step or 2 step, whatever maybe. IC means integrated circuits fabrication. Masking good, doping very good, etching fine. This thing is what expected, right? You should have something, and if you are able to communicate with me, means that will be better for further communication. Otherwise, it will be a single side of communication. It will be simply, finally, it will be going to be boring. Okay. The core steps we can say it as epitaxial growth, thermal oxidation, photolithography, etching, dopant diffusion, metal evaporation, and electrical testing. So these are the words I'm used to get depend upon the things happening in the laboratory. Okay. The IC manufacturer, for example, if you are considering the same the Snapdragon 845, the Qualcomm Snapdragon 845, or the Qualcomm 730, that IC will be manufactured in this kind of series of steps. The material might be different. Okay, the material used for that semiconductor might be different, and the process remains to be same. Epitaxial growth, that is suitable selection of first wafer. First one is the suitable selection of a silicon wafer or some other wafer. Then is the epitaxial growth. From that growth, how you are going to be overlaid with an oxidizing material, that is thermal oxidation or some other oxidation techniques are there. Then photolithography or separate lithography concept is there, combined with etching, dopant diffusion, metal evaporation, and finally is the electrical testing. Yeah. So first, what is that epitaxial growth? They are going to create a substrate. They are going to create the substrate. Substrate means silicon material. If you are having a P-type substrate, means you are going with the N-type material. We are going with the N-type material. So now I have started with the thermal oxidation only. It's a dominant semiconductor. Silicon is a dominant semiconductor used in the integrated circuit processing due to the ability of form robust. Okay. Also, multiple purpose of fabrication of IC. So, the diffusion barrier for selectivity doping, dielectric, it can act as an insulator, then passivation and protection of the silicon surface. The passivation means the final layer what we are going to be pasted. Okay. So, silicon is the dominant semiconductor used in integrated circuit processing. That the diffusion barrier for selectivity doping, then dielectric for most devices, then the passivation. Then the oil for a particular semiconductor processing, cleanliness is important. Before oxidation, you should remove the contaminations, that oil materials or some of the traces of metals, alkalis or alkalides, whatever the materials that is combined over there, you should remove that. Okay. So this is the thing that is happening in oxidation. How it is happening? The high temperature furnace of 900 degrees Celsius to 1200 degrees Celsius. Okay. 900 degrees Celsius to 1200 degrees silicon plus oxide. We are able to get silicon oxide. Okay. So silicon oxide is, that is wet process, wet oxidation. Okay. The silicon plus water is water vapor. Hey, sorry, that is a mistake. Silicon plus dust, oxygen is dry process. Okay. Silicon plus water, that is a steam-like concept. That is a wet process. The lifetime and the quality, superior quality will comes in this process, silicon plus oxide. That is dry process. Okay. The wet process, the quality will be somewhat less. So example of patterning of silicon oxide. So this is the substrate. First you are having the wafer. Then you are going to paste with the substrate with the oxidation and deposition of negative photoresist. So silicon oxide you have been pasted. Okay. Then you are patterned with a photoresistive material at a mask etching. This is what's happening in the photolithography. Now we are going to see the photolithography. So after oxidation, we will completely cover the silicon dioxide, prevent dopants from reaching. So we want to create some space for reaching the dopants. Okay. So we are using ultraviolet rays. a sensitive photoresistive material. Ultraviolet rays, that is a sensitive photoresist material to coat the wafer. An alignment or illumination system to expose the photoresist. Clear? That mask or reticle with a desired circuit pattern that allows only UV light. So there is a band pass filter. There is a band pass filter that is used to allow only the UV rays. Okay. The acid to etch the oxide to the open is created in the PR mask by photolithography. By photolithography. Clear? The selective removal of the oxide is performed. So by means of ultraviolet ray, the masking is the process of covering that silicon oxide layer. That layer will have the intensity or the tendency not allowing the doping to happen, not allowing the doping materials to happen. So here we are using some of the techniques, that photoresist or some of the techniques to make the doping happens. For PR coated wafer like film, okay, mask aligner is like the camera. Then the mask or reticle is subject to the picture. So it is like a coating with the film-like material. If you are having a thin nanometer of, because nowadays the Qualcomm Snapdragon, the processor comes in the range of 11 nanometer to 7 nanometer. Snapdragon 665, around 10,000 to 15,000 mobile. That range itself is having 11 nanometer chipset. Okay. When coming to high-end 845 or 855, nowadays 865 is coming. In that processor, we are having around 7 nanometer thickness. So you want the precision and accuracy. That is very, very, very much needed. How accurate you are and how particular about you are that. So that is much, much needed. So here is the circuit diagram in the form of computer-aided design. Okay, full adder layout. So here the class we are using the computer design for software. That software is used to compress the device in a similar way in the nanoscale. Nowadays it is comes under the region of nanoscale, where the transmission will not be affected by the interconnections or some of the interference. Okay, so mask in the photolithography is very, very, very efficient, and how the circuit is opening or working depends upon this concept. So PR applications. So here we are using some organic polymer sensitive UV light too. This is the things that is happening in the lab. Okay, they are exposed to green, blue, violet or ultraviolet rays. Here we are exposing to green, blue, violet or ultraviolet rays. The photoresist is a small puddle in the center. Puddle is nothing but some elevation that our wafer spins over there, and they are able to form the photoresistive masking. They are able to form the photoresistive. This is the real thing happening in the laboratories. Okay, that is laboratory. Then the alignment exposure. Loading PR coated wafer is in the Ultratech 10,000. That is a device. Okay, the repeat position alignment system. That device is used to maintain that wafer. That is very, very, very thin material. That is having a very, very thin material. I had taken these pictures from the internet only. Okay, internet. I had taken these kind of things from the laboratories that are existing in abroad. And one more thing I want to mention here: well sufficient or well sophisticated IC manufacturing company or some of the industries not existing in India till date. Okay, IC manufacturing, the board, PCB design, and all those things has been happening. This kind of sensitive nanoscale production ICs manufacturing is very, very less. And that if some companies are there, the sensitivity and the quality of that thing coming out from there is not that much efficient when compared to coming from the abroad. That's why we Indians still not having a separate mobile company at our India. Even though we can think about Micromax or Lava, some of these guys are purchasing some of the components from abroad and assembled somewhere else and giving us a packet. Okay, and now the same thing is happened by the Chinese market product providers. For Oppo or Redmi or Realme, they implemented their factories in India itself, and they do the same here itself. They are also purchasing the processor from Snapdragon or MediaTek or some other way, and they are assembling all these parts. They are getting the cameras from Sony and all those things. Alignment or the package is happening, and you are getting some mobile. Clear? So that is the thing. We are not having a separate processor producing company. Processor producing, that is different. That is different from that assembling. Okay, the processor producing concept companies there means the demand is more. So the development So we are having that two types. The wafer is exposed to UV light through the mask, as it can be seen in the PR, that is photoresistive method. So these two methods are used for the development of the wafer. So after etching is nothing but the previous steps. You are using the oxidized wafer, some dust particles or some unwanted materials are ranged over there. So this oxidase, we want to remove the unwanted materials very over there. We are using the etching concept. We are using the etching concept. In this diagram, this is the real wafer after 100 millimeter diameter. This 100 millimeter diameter device, we are able to get a processor, a chipset. What we are going to design will be seen in the laboratory. Okay, ma? Next is the dopant diffusion, pre-deposition. I am representing here is a pre-deposition. The goal of the dopant pre-deposition diffusion is to move dopant atoms from source to the wafer, then allow the dopants to diffuse into the wafer. So here also the silicon, one order the dopants to move in the silicon, the temperature should be maintained from 900,000 to 200 degrees Celsius. From that only we are able to come with this kind of process. So for the dopant diffusion by drive method, one is called the pre-deposition, another one is the drive method. Here the major difference is there can be done in the same time. Parallelly, we are able to do the processing and the etching. Okay. Repeat the process. What are the processes already? Epitaxial growth, then that what is called photolithography, then etching, then what is called diffusion. We should do all the things: oxidation, photolithography, etching, and diffusion. It should be due until the iterations. So how much iterations if you are going, the quality will be laid over there. Okay. So first masking, mask 2, mask 3, mask 4, mask 5. The final outline we are going to get by means of applying the metallization. So here the mask 1, mask 2, mask 3 they are applying the photolithography concept and then etching. Masking, etching. And finally we are going for the metallization. So metallization in there we are going to make the anode should be binding with some material, metal, conductive material to communicate with the external devices, right? Communicate with the external devices. So this is the completed wafer results from the initial oxidation to the metal definition, final metal evaporation. Then this particular chip will go for testing with respect to the software what they are processing over there. From that process, they are able to get with the production panel. Production panel is approved, the quality is checked, then they are going for multi-number of production and giving to the consumers. Clear? So this is the steps I am going to repeat once again, guys. So first one is what I am going to mention here is the oxidation. Before oxidation, the selection of wafer. So after oxidation, we are having two types of oxidation. One is dry and another one is wet. Dry is having the better quality. Okay. And next we are going for the substrate. Substrate will be oxidized. Oxidized will have the UV pattern. The UV pattern for the masking. From that masking, we are hardening the resistor material. Then we are going for etching. After that etching, we are having the substrate and the silicon dioxide. And some area there will not be any the silicon dioxide material. The silicon dioxide will act as a dielectric. We want to remove the dielectric so that we are able to make that silicon wafer to communicate with the doping materials. Okay. Photolithography. Photolithography are the two types. One is photoresistive material, another one is mask material. So we are applying by means of UV light. We are able to get the photolithography. That material should be etched. Etched is nothing but the removing of the unwanted materials. So finally is the dopant diffusion, that is prediction. That is the pre-deposition method. Another one is the dry method. Here the parallel the process is happening. So depend upon that we are repeating the process. That is oxidation, photolithography, etching and diffusion. We are repeating the process to get more iterations to get the better quality. Okay. Then we will go for metallization and we will get the completed wafer, which will be tested, and after that we are getting the 100% accurate results, then it will be go for the production. Clear, guys? Okay. So now we are going to the problematic part from the theoretical part. So the question is, in IC technology, a dry oxidation. Okay, as I mentioned, a dry oxidation as compared to wet oxidation produces, which one is better? A dry oxidation, I mentioned earlier. If you come across the class, you will get the answer right now. Which one is better, dry oxidation or wet oxidation? Which is having better quality? Dry oxidation. Good. So dry oxidation is our superior quality oxide with higher growth rate. Okay. Compared as dry oxidation as compared to wet oxidation. So dry oxidation will be better. So it will have superior quality. But we are having two choices: superior quality oxide. Here also superior quality oxide. It's a higher growth rate and lower growth rate. Here the answer is oxidation with respect to wet will be a easier process and the quality will be somewhat less. But the oxidation with respect to dry process is taking time consuming. This is taking more time consuming, but the quality is wet. So the answer is superior quality with lower growth rate. Superior quality with lower growth rate. Next one, the primary reason for the widespread use of silicon in semiconductor device technology is abundance of silicon on the earth's surface, large band gap, favorable properties of silicon oxide, lower melting point. What will be the answer? Primary reason for widespread use of silicon in semiconductor device technology. What will be the answer, ma'am? Abundance of silicon on the surface of Earth, large band gap of silicon, favorable properties, lower melting point. Answer C. Favorable properties of silicon dioxide. Good, correct. Can I get the explanation? That's the correct answer. The thing is, abundance of silicon means germanium is also abundance. Then why we can't go for this germanium? That is not the reason. Okay, the abundance of silicon, germanium, gallium arsenide, so many things are there. Okay, large band gap of silicon is comparison to germanium. Oh, if large band gap means comparing to silicon, sorry, comparing to germanium, silicon is better. Comparing to silicon, gallium arsenide is very, very better. Okay, large band gap. So that also not a feasible one for this particular question. Next, favorable product silicon oxide. Yes, silicon dioxide can be acted as a dielectric. It can be acted as an insulator. That particular material can be acted as an overcoat sealing. So this is the one thing, that combination of silicon with oxide and not creating any rust type material. Rust means if you're having a ferrous type material, a conductor, if you're oxidizing means it will be generating a rust that will not be useful, further useful, right? But this particular thing is not like that. The favorable property is silicon dioxide, it won't be get rusted after oxidation. So the answer is favorable properties of silicon dioxide. There are two photolithography systems, one with light source of wavelength 156 nanometer, okay, and another with light source of wavelength 325 nanometer, right? Both photolithography systems are otherwise identical. All the other systems are identical. If the minimum feature size that can be realized using system 1 and system 2 are L minimum 1 and L minimum 2 respectively. The ratio of L minimum divided by L minimum 2. Okay. So there are two photolithography systems are there. Their wavelength, that is lambda 1 and lambda 2, are only different, but the system is identical. In all other aspects, the system is identical. So what they question, the minimum feature size ratio, L min by L2. So first they have provided for system as L1 is lambda 1 is equal to 156 nanometer, lambda 2 is equal to 325 nanometer. L minimum 1 and L, that is the minimum feature size. So we want to find the ratio. The L minimum formula is K lambda divided by N. K lambda divided by N. So L minimum 1 is equal to K lambda 1 divided by Na, L minimum 2 is equal to K lambda 2 divided by Na, because the system is identical. Got it? Because the system is identical. So K and Na will cut out. Remaining one is lambda 1 divided by lambda 2. So 156 divided by 325 is equal to 0.48. 0.48. Clear? You got the answer. So this formula is depicted from the theoretical point of view. So the feature size is equal to K, the like constant into lambda 1 by doping concentration divided by, that is doping concentration consists of charge particle acceptor and donor. N is donor and A is acceptor concentration. So K into lambda 1 divided by N. Clear one? Next, in MOSFET fabrication, the channel length is defined during the process of MOSFET fabrication. Channel length is defined during the process of. Can I get an answer? MOSFET chip fabrication, the channel length is defined during the process of. Any answer, guys? Some random suggestion? No. Okay. A MOSFET fabrication, a MOSFET IC fabrication, channel length. We are not bothering about everything. The channel length is defined during the process. Isolation of oxide growth. What is that? Oxide growth means you are oxidizing that particular silicon by a layer and you are separating for different oxide growth. Okay, N type, P substrate, and different layers will be there. So there is no range for channel length. There is no role for channel length. Then channel stop implantation. Then channel stop implantation. Here the work is, if you want to have a specific channel length, there will be some dimension. If the channel length is not defined, it will be overlapped because a 10 nanometer chip will have lakhs of MOSFET devices. Lakhs of MOSFET devices. So if you are not defined the channel length before the channel stop implementation, then there will be a problem occurs, a major problem occurs, that channel stop, the overlapping will occur. So, okay, that is the answer. Then comes the polysilicon gate sputtering. So here we are not bothered about different types of material, polysilicon, different gate materials or different types of materials. So there is not an answer related to that. Next one is lithography step leading to contact pads. Yes, photolithography without correct masking, if you are doing so means it will be lead to a contact between that oxide layer and the substrate. Clear? So lithography, that process is fine, but here not bothered about that contact parts. Okay, here we are only bothered about the channel length. So this is also not related to this one, but this is the correct statement. Lithography steps leading to a contact parts. There might be cause some problem in the fabrication. Then that will be correct answer. Okay, but with respect to channel length, the channel stop implementation is the answer. Okay, if so, you should give me the answer for this one. I will give some 5 minutes. If P is passivation, Q is N-well implant, R is metallization, and S is diffusion. That is also same diffusion. Then order in which they are carried out in standard N-well CMOS fabrication process. Once again repeating, if P is passivation, if P is passivation, then what comes? Q is well implant, R is metallization, and S is source drying. And the final one is diffusion, source drying diffusion. Then the order in which they carried out in standard N-well CMOS fabrication. CMOS fabrication. What will be the answer, ma? First, you should understand that it is defined with respect to a fabrication. Fabrication means there will be a series of substrates. Sorry. There will be a series of substrates, right? So, depending upon that, you should define. Otherwise, it will not get the meaning. No idea. Okay. So here we are having some substrate. Let it be a P substrate. Okay, guys. P substrate. So CMOS fabrication. CMOS means NMOS and PMOS both you can be processed in the same substrate material. A twin tub process. A twin tub process is a material we are able to generate NMOS and PMOS in the same CMOS type of material. Okay. So here, first one is we want to implement the well implantation. A well implantation. This is nothing but Q. Okay, here you are giving some N type. Here you are giving some N type. And next we are having some source and drain diffusion. That is a junction you should form. Source, drain, and that should be connected with some of the substrate materials. Clear? So this one is N-type material, this is P-type material, and here we are having some source. Okay, source and diffusion. So first P substrate. Now first one is P substrate, then we are having the Q well implant. This is the first step. Second one is source and drain diffusion. After oxidation, we are having the diffusion. Okay. Then we are going to oxidize this layer. We are going to oxidize. If you want one layer or if you want two layers, you can oxidize it. They are not mentioning here oxidize. After that oxidization, you are going to make some contact by means of some electrodes. So you are going some metallization. Between the source or gate, you are having some metallization. So that one is R here. Then metallization, we are having the passivation to remove the extra etching or extra components that are available over there. So first one is Q, second S, next R, next P. Sorry. First one is Q, next one is S, next R, next P. This is the process. So depend upon the process of fabrication, IC fabrication, they are provided one straight question. You understand? Clear, guys? If P is passivation, Q is N-well implant, and R is metallization, and S is source or drain diffusion. Then the order in which they are carried out in the standard N-well CMOS fabrication. So as I mentioned in the twin tub, no. So in CMOS fabrication, we are able to have, that is N-type means, here you can separately have P-type. Okay, here also you can have the N-type and P-type substrate layers. Clear? This is the advantage of twin tub process, where the CMOS device you are able to produce both the P-type and N-type material, PMOS and NMOS at the same time. Clear, guys? So right now I come across the end of the session. So if you have any doubts, I have given enough time, we can ask it. Guys, I think in this section we have less problems. Numerical problems will be less. Analytical problems will be more in the gate point of view. Okay? Okay, students. I will go from the first starting. Sorry, no? Let's go. I'll go from the starting. So today we got the revision. I had less response, so it's really coming thing. So today's lecture will shoot LED, photodiode, solar diode, and the tunnel diode, and the integrated circuit processing are the different types of processing for generation, and the twin tub process of CMOS. Okay. So what is LED we studied? So the working principle of LED, then the animation, right? If possible, I will show it to you. 1 second. It's not connected. So the application of LED diodes. Next, we are going to deal with the two more questions, diodes. So this is the Zener diode, the voltage regulator. Varactor diode is a variable capacitor. Then Scotchy diode is a high frequency switcher, then the PIN diode. Okay. Then there comes the PN junction diode where the light is converted to a voltage or current. Okay. It comprises of the optical filters or built-in lenses. So the process here is reverse bias configuration. It is in the reverse bias configuration. That is the much photoelectric happens in the reverse bias configuration because LED that happens in the positive bias configuration. So in the reverse bias junction, we are going to use the photo generator. Okay, in the space charge limit area. So in the space charge limit area and the neutral area by means of diffusion process, we are able to generate. Then there are two conditions: one is short circuit PN junction, and another one is open circuit PN junction. Okay, so this is also not running. These are the applications. Then the question regarding that photodiode. We analyzed photodiode and tunnel diode also. Then the problem with respect to that of the electric photon energy and the wavelength. How the photon energy and wavelength are related. Next, the power incident on the that is the photodiode and how it is the responsibility is going to find the current. Okay, then the next concept is solar cell. So solar cell we are having the two major formulas, that is ID is equal to IO e to the power of VT divided by VT minus 1 minus IL. So VOC is equal to VT log of IC plus IO plus 1. Working principle. So that is that recombination pair will split up, right? So in the fourth quadrant only it is okay as a solar cell. In the third quadrant it will be working as a photodetector. So fill factor, so it has the fill factor, the types. So crude junction cell will have greater than 20% of efficiency compared with the older existing solar cells. Okay, then the problems. Next, the steps of processing or production in the integrated circuits. It starts from epitaxial flow through electrical testing. Here, so first thermal oxidation, because selection of vapor is a basic process. So I didn't mention here. Starting with the oxidation. So oxidation, two types of oxidation. One is dry and wet oxidation. Dry oxidation is better when compared to the wet oxidation. Then for the pattern of photolithography and etching, so UV light we are using for masking. So during the masking process, we are able to generate a full layers, and we want to remove that gap between the oxidation to make the doping to happen. So by means of photolithography concept, we are able to make a doping. Next one is etching. So due to the same process, some unwanted materials or some metal features will be there. So you want to remove that. Then the oxidation, photolithography, etching, and dipping, the same process will be continuously reviewed for different iterations, so that we are able to get the best wafer. The completed wafer will go for testing, and we are able to produce the chip that is used for the consumer purpose. Then the problems. So these are the problems that are mostly related with the analytical point of view when compared to the problematic point of view. Okay. This is my number, name. Please, guys, make use of it. If you have any doubts, you can contact me at any time. Okay. Can I wind up the session? Any doubts, Suresh sir? Okay, students, thank you. Please don't consider GATE as a simple one. Make use of these kind of opportunities and make the time fruitful way. Okay. Photo current is a reverse current or diode current. So here we are. Here you are able to say that photo current is different and diode current is different. So photo current what we are representing here is nothing but a reverse current. Photo current what we are representing here is a reverse current. Clear? Clear, Nishani? Any other doubts, ma'am? Okay, thank you guys. I'm winding up the session. Thank you for your patience and listen.